Okay, hello guys. Thanks for uh, coming back to another energy, power, and propulsion lecture. So I couldn't record this lecture in the class yesterday, and by yesterday I'm talking about September 14th. So today I am recording a fully online lecture for those of you who couldn't make it to class on Monday, and for those of you who are completely online. So we are going to continue the discussion, and we are going to talk about a third method in engine thrust calculations. This third method talks about the impulse calculations and uses impulse to get to essentially the same equations we have already seen, but along the way we will see some different concepts and some new methods. So let's take a look at the engine again and see what do we have. At station 0, we have 9 stations. If you recall, we always have the 9 stations. We have the station 0 here, which talks about the ambient conditions. Okay, then we have the inlets. We have whatever we have in the engine, and we call it stations M. And then we have the exit condition or the outlet condition 9. So if you want to find the net propulsive thrust, and this is we're talking about the installed thrust here. Okay, the net propulsive thrust is going to be your gross thrust minus the ram drag, which is the uninstalled net thrust, minus the drag due to inlet total pressure loss, minus the additive drag, plus the lift suction force, which the combination of two is called the spillage drag, which we talked about in the previous lecture, minus the aft end drag. Okay. So to write the impulses, as we said, we want to talk about the component impulse. When we are talking about the component impulses, it means that we want to go into the engine, right? So we want to talk about the gross uninstalled thrust, and we want to quantify that as using the thrust, using the impulse of each component. So inside an engine, we have 9 stations. Then we are showing the main ones here: the inlet stage, the compression stage, the burner stage, turbine stage, and after turbine stage. We call it after burner stage, right? And for each of the stage, we can have a thrust for the inlets, for the inlet condition of each station, and the outlet condition. And if you recall the forces from the previous chapter, the force that is being applied here can be calculated using the the changes in thrust, impulse, sorry. So for example, if you're looking at the compressor section, your F of compressor can be calculated by I2 minus I3, which is the inlet impulse minus the outlet impulse. We can do the same thing for burner stage, which is I3 minus I4. Same thing for the turbine stage, I4 minus I5. And the same thing for the nozzle exchange, which is I5 minus I1. So if you plug those in, we also have the diffuser stage that I have not listed here, but which is I1 minus I2. So the total engine force can be modeled with the summation of all of the forces, the component forces, and then we can replace the component forces with their respective impulse difference. So if you plug those in, simplify the equation a little bit, you'll get to I1 minus I9. And this I1 minus I9, we already know how to calculate thrust. We already have the equation. So I1 is going to be equal to M dot 1 V1 plus P1 A1 minus m dot 9 v9 plus p9 a9. So we will be able to calculate the engine force in the actual direction using the inlet and the outlet condition. But we would rather have the ambient condition. So we would rather have replace this with the ambient condition instead. Okay, so how can we turn this inlet to the ambient condition? We essentially have to take a look at what happens from station 0 to station 1, which is the inlet. We, of course, from the previous discussion, we, of course, know that this stream tube is changing, the area and the pressure of this stream tube is changing. So that should be something that we have to include in our discussion. So, yeah, as we mentioned previously, the internal thrust can be calculated using the outlet and the inlet conditions. That's the force inside the jet engine, right? Whatever force is generated inside the jet engine, we call that internal thrust. But moving on, we know that the area and pressure changes from 0 to 1. So if you essentially write the momentum in the x direction, momentum equation in the x direction, momentum in the x direction, this is what you're going to get, right? The momentum at the inlets minus the momentum at the zero station, this is going to be equal to the summation of forces. So we have a force at the inlet, the pressure force at the inlet, and also the pressure force at the zero station, which is there because of this pressure difference, right? And we also have this area change, which has a pressure distribution by itself, right? At each point, we have a pressure P. We can call it P of X, whatever. Here we have called it P. And then to find that force, you essentially have to take the integral of the pressure distribution here with respect to the changes in area, the respective area. Okay. And we call that part, this part, is actually can be represented by your additive drag. So using this equation, we can replace m.1v1 plus p1a1, which we have here, right, with this term that relates your internal thrust to the zero station, and it just adds an additive drag. So your internal thrust eventually will become this. It's going to be m.9 v9 minus m.0 m.0 v0 plus p9 a9 minus p0 a1 plus the additive drag. Okay. And you always have to keep in mind that the integral of the pressure distribution from the inlet for all of the jet engine, all of the stations, eventually is going, the surface integral is going to be end up to be 0. Okay. We also have some other forces that are present here, as we have discussed. We have the nozzle force, which is the force that is being applied to the outside of the jet engine. That includes the viscous forces and the pressure distribution, so the shear forces and the normal forces. And there is a pressure distribution that's going to change, as you can see in this picture here. So we have to take that integral with respect to the changes in area, and we have to add the viscous forces as well. And we also have the nozzle lift forces, As you can see here, we have the lift suction force, lift thrust force, and all of the side forces and thrust force. All of those forces are there, which must be equal to the negative of the additive drag based on the formulation. And you plug those in, this is what you eventually are going to get for the total installed thrust. So this equation we have seen many times so far. This represents the uninstalled thrust, and from this perspective, we can actually include all of the losses, if you will, the viscous losses and the pressure, the normal losses, if you will, as the installation drag. So a subtraction of the installed thrust from the installation drag will eventually give you the installed thrust. So we have this final equation for the installed thrust from another perspective. So far, we have seen three different perspectives, and all of them went to the same conclusion, but a little bit of a difference in how they look at the installation drag part. But eventually, they will give you the same results. Moving on, we want to have a very we want to have a very small discussion on the rocket thrust. So when dealing with rocket, we are essentially dealing with the same thing as an air-breathing engine with a sealed inlet. So there is no air coming in. We only have the exhaust condition, the exit condition, right? And this is how a rocket essentially looks like. You have your payload, your guidance, navigation, and controls in the front. You have the oxidizer, fuel tank, and all of the fuel system, if you will. And then you have your engine, your rocket engine, which you supply the fluid. You have the combustion chamber happening. There is no inlet. There is no nothing. And that combustion chamber, the combustion is going to produce the thrust for you in the rocket. So essentially, if you look at this, the only difference this has from a macro perspective, from a thrust generation perspective, with the air-breathing engine is that it doesn't really have the inlets. Okay, so we can essentially, let's go back to the uninstalled thrust equation. These were the outlet conditions. These were the inlet condition or the ambient condition. So this part will go to 0. It's not there. All right, but the ambient pressure is always present. This pressure difference doesn't really go away. Just have to keep that in mind. Okay. So this is what you're going to get. This is m.9 is going to be a summation of the oxidizer mass flow rate and the fuel mass flow rate multiplied by your exit velocity plus the pressure difference between the exit pressure, exhaust pressure minus the ambient pressure multiplied by the exit pressure, exit area. Sorry. So this essentially is telling you that your rocket thrust does not depend on flight speed. Okay, it's a very important conclusion, right? This is not a correct conclusion, but it's a very important conclusion that in your equation you don't have a component of flight speed, but you always have to keep in mind that the flight speed is definitely going to affect your ambient pressure, right? So the rocket thrust does not directly depend on the flight speed, but indirectly it definitely depends on the flight speed. Okay. So moving on, we discussed this. Moving on, eventually this is the final discussion we're going to have, and this came on to be a very short lecture. I mean, we have a lot of discussion left, but it's not going to be 1 hour and 15 minutes. It's not going to be a 1 hour and 15 minutes lecture. So yeah, it's not gonna be a 150-minute lecture. Let's move on. The final thing we want to talk about, the final formulated subject that we have here, is the performance parameter in an air-breathing engine. We have different performance parameters that are very important for us uh, in analyzing and comparing different engines, jet engines, right? We have the specific thrust, we have the specific fuel consumption or TSFC, and the specific impulse, we have the thermal efficiency, and we have the propulsive efficiency, and we have the engine overall efficiency. And we will talk about its impact on the aircraft range and endurance. Okay. The first thing you want to talk about is a specific thrust. You have to keep in mind that mass flow rate directly affects thrust. But the thing is, we can always change the mass flow rate by changing the air intake size, right? So the mass flow rate itself is not a real design parameter because it's a parameter you can always play with, even after designing your engine with just like variable size intake, variable intake size. And so, which means that your engine size, it also means that your engine size is a scalable parameter. So it's not really the mass flow intake. It's not really a real design parameter, if you will, right? Because you can always change that after the design, and you can always change your engine size and will change the mass flow intake. So a better look at the design performance parameter, if you will, that will enable a better comparison between two different designs is the specific thrust, which is the ratio of thrust to air mass flow rate, right? So this is going to be the air breathing engine performance parameter number 1, right? Which is your F, your thrust normalized by the air intake, the mass flow rate of air. It has a metric unit of Newton seconds per kilogram, or a British unit or royal unit of pound for second per pound mass. We can always non-dimensionalize this specific thrust by dividing it by the speed of sound, the air speed of sound at a specific altitude and at a specific temperature, right? So this is your first parameter, a specific thrust, and we already know why we are going to use a specific thrust. The second performance parameter is thrust-specific fuel consumption. So essentially, keep in mind that before moving on to the second one, keep in mind that we always want to maximize this specific thrust, right? So we want to get the most thrust for the lowest air intake, right? And the second parameter we need to talk about is the thrust-specific fuel consumption, or TSFC. Right? This TSFC is essentially, as is obvious from its name, it's the amount of fuel you are going to use to be able to generate some thrust, right? A certain amount of thrust, right? Of course, we always want to use a smaller amount of fuel to generate more thrust, so we want to minimize this. And it's a very important parameter when dealing with commercial airlines. Mainly because when you're dealing with the military aircraft, your fuel consumption and being environmentally friendly is not one of the, or being even cost efficient is not one of the main concerns. There's other goals that are defined for military aircraft. So a specific thrust that TSFC is very important for commercial airliners, and you always have to be mindful of that. Yeah. Moving on, you may want to ask, okay, so if TSFC is not important for military aircraft, what is important for military aircraft? What is the important component for the military aircraft when it comes to the comparison of thrust and uh, fuel mass flow rate, essentially? That is going to be your specific impulse that we have here. That is defined as a thrust generated per amount of fuel spent multiplied by the gravitational acceleration. Okay, and if you're dealing with a rocket, your specific thrust is essentially going to be your specific impulse should be calculated using the fuel mass flow rate plus the oxidizer mass flow rate. So a specific impulse for an air-breathing engine is essentially your thrust divided by mass flow rate multiplied by the gravitational acceleration. And a specific impulse for your rocket is going to be your m dot p, which is m dot f plus m dot ox in the denominator multiplied by g, and in the numerator you have the f. Okay, this is a very useful performance parameter. That essentially is going to be telling you how much power you can generate for by spending a specific amount of fuel weight. Okay, but the main reason it is very useful performance parameter, it doesn't really matter if you're dealing with a military aircraft or commercial airlines, is because of its units. Its units is in seconds, right? And the seconds, this unit is the same for the British system and the SI system, and the SI, right? Which means that it doesn't really matter what kind of a unit system you have used for your calculations. If you find a specific impulse of your design, you will be able to compare your design with other jet engine designs universally, which makes it a very common and very useful parameter in designing an aircraft. Okay, but the next thing we want to discuss is the next performance parameter we want to discuss is the thermal efficiency. Thermal efficiency can be defined as the amount of kinetic energy you can extract from the energy that is produced by burning the fuel that is produced in the combustor, essentially, right? So delta, for most cases, it's going to be delta kinetic energy, the rate of change in kinetic energy, over the total heat input of the system. So total heat input of the system in the numerator, this is something that's generated in the combustor within the engine, right? It can be calculated by the amount of fuel that is put in and the total heat rate that you are getting from that combustion, right? From the combustion of that specific fuel, right? And this is a parameter that you usually can get for the fuel that you are using, the QR, right? And a specific, the rate of change of kinetic energy, at this point you are already pretty familiar with this, right? It's going to be m squared, m dot v squared over 2, right? And the total kinetic energy change is the kinetic energy change between the station 9 and the station 0. So we can come up to this final equation for the thermal efficiency calculations. You have to keep in mind that we are not losing the energy that is not transformed to the kinetic energy. We are essentially wasting it. So what it means is that whatever energy generated inside the combustor that is not transformed to the kinetic energy is going to be wasted through exhaust. So we're going to have a very hot air coming out of exhaust, and we can always recover some of this wasted energy, but different methods. We had a discussion in class. For those of you who were in class, it was a very interesting discussion. So I encourage you to think about the methods that you can use to recover this wasted energy, which means that you want to cool down the exhaust air. Okay, and but for some cases, the most of the energy is not going to be transformed to kinetic energy. Some of the energy is going to be transformed to the shaft energy that is going to rotate the propeller or for other different purposes, right? So sometimes if you have a shaft in your engine that is eating up 50% of, for example, 50% of your extracted energy, it's extracted mechanical energy, you have to include that in your thermal efficiency calculation. And if you're dealing with a turboprop, like this case, or turbo shaft engine, you shouldn't even include the kinetic energy changes in your thermal efficiency calculations, because it's going to be the kinetic energy jump is going to be so small compared to the energy you're giving, the mechanical energy you're giving to the shaft. And we have two examples of the gas turbines that include the shaft, and most of the energy goes to the shaft. Most of the mechanical energy, extracted mechanical energy, goes to transformed mechanical energy, goes to the shaft instead of the jump in the kinetic energy. Okay. One of the methods that we can recover some of the wasted energy is through a regenerative cycle. A regenerative cycle is essentially putting a heat exchanger at the exhaust, before the exhaust, right, in the exhaust pipe, that is going to heat up the fluid, the air that is going into your combustor. Essentially, it's going to help the combustion process, and it's going to reduce the amount of energy you're going to need to have the combustion. Okay, but there always, with all of these methods, what you always have to be mindful of is the answer to this question: will our gains outweigh our losses? So that's something you always have to be mindful of. Like putting a heat exchanger, of course, is going to decrease the amount of thrust that you can generate, right? So you should see which is your main concern, what you want to do, and you always have to be able to answer this question with a yes in your design. If you're including a new, if you're adding a new component to your design, and you always have to keep in mind that 100% efficiency, it is not something that is possible. Okay, so something else that we have to talk about is the difference between the thermal efficiency and the propulsive efficiency. We have these two kinds of efficiencies in jet engine design. One of them is the thermal efficiency that we have discussed, that the ability of your jet engine to extract more mechanical energy, more and more mechanical energy from the generated heat, or from the heat input. When you have higher ability of extracting more mechanical energy from the heat input, it means that you're more thermally efficient. But we also have another efficiency system, efficiency thing that we have to be mindful of, and that is called propulsive efficiency. And that's the amount of kinetic energy that is, or the mechanical energy that is, can be transformed to thrust power, right? So in this analysis, we are comparing the thrust power, the final thrust power you get from your jet engine, with the mechanical energy that you have over there. Okay, The propulsive energy can be calculated using this equation. We have the thrust power at the numerator, and we also have the kinetic energy. In this specific case, we have the kinetic energy in your denominator, right? We can make some assumptions and simplify the equation a little bit. We can assume that it is a perfectly expanded nozzle, which means that in your thrust you won't have any pressure component, and all of your thrust component, uninstalled thrust component, is going to be your velocity components, right? If you plug that in, we already know that how to calculate the energy, the kinetic energy jump, and do a little bit of simplification. This is the propulsive efficiency equation you are going to get. And this ratio is your jet velocity versus the flight velocity. So in theory, this thrust can be 1 when your jet velocity is equals to flight velocity, but this is not something that can really happen in the real world. Okay. What if your mechanical energy is not dominated by the jump in the kinetic energy? In that case, you have to include the shaft power, of course, that we have seen before. For a turboprop in which the kinetic energy is negligible compared to the shaft power, we can only include the shaft power. The same is for the turboprop engine, and eventually you are going to only use the propeller prop power in your propulsive efficiency calculation. Okay. The reason this shaft power is very important, is that because of the large diameters of propellers, we have to reduce the rotational speed. I'm sorry, this is the reason for it. Okay. So we have a lot of. Let's move on from here. Okay. We also have to, in the turboprops, we also have to include gearbox efficiency, and mainly because we have to be able to change the amount of power we are giving to the propeller. So we want to be able to control the rotational speeds, and the only way you can control the rotational speed, and one of the ways we can control the rotational speeds is through a reduction gearbox. Sorry. That reduction gearbox itself may have some losses, so we have to include a gearbox efficiency, which is going to be the total power that is going to be to the shaft. That's going to be your propeller divided by the total shaft power of the turbine. Okay. But just calculating each component's efficiency is not going to help us. We want to find a final we want to be able to calculate the final efficiency of the system, final jet engine efficiency. To do so, you simply have to multiply all of the efficiencies you have. Let's say if you're only dealing with a jet engine that doesn't really care about the shaft power, meaning that most of its energy change goes to the kinetic energy jump. Most of its mechanical generated mechanical energy goes to the kinetic energy jump. You just have to multiply the two efficiencies, propulsive efficiency and thermal efficiency, and you can always simplify the equation that you have, meaning that you can remove the kinetic energy from the system. This is what you are going to get as the overall efficiency of an aircraft engine. But the efficiency itself can affect the range of an aircraft and the endurance of an aircraft as well. The range and endurance are topics that we discuss in detail in flight mechanics, flight and orbital mechanics course. But I'm just going to give you some equations that is going to help you calculate the range of an aircraft. So you just, whenever you were asked to calculate the range, the only thing you really need to do is to plug in the values into these equations. Okay, so the range is related to your overall efficiency using this equation. Range is through the Brugget equation, right? Range is equals to Eta naught, which is your overall efficiency, QR, total energy, thermal energy input of the system, over G naught, gravitational acceleration at each point, a lift to drag ratio multiplied by the Wi over Wf. So Wi is going to be your natural log of Wi over W. Wi is going to be your initial weight, and Wf is going to be your final weight, right? Final weight is essentially the same as initial weight minus the weight of the fuel that you have burnt. Okay, and we can play with this equation a little bit to get to this equation for the range. That's going to be relating your range to the thrust, the flight speed, the mass flow rate, fuel mass flow rate, QR again. You can always simplify the QR as well. And lift to drag ratio, natural log of the weights, the initial and the final weight, right? Eventually, the equation, you can get this equation that relates to the range to the Mach number, the flight speed Mach number, lift to drag ratio, the speed of sound, and the gravitational acceleration, and TSFC, that's the specific fuel consumption, natural log of Wi over Wf. As you can see, your aircraft is related to your flight speed and the lift to drag ratio, as well as 1 over TSFC. We can do the same analysis for an aircraft endurance. Aircraft endurance is defined as R divided by the range divided by the flight speed, which is essentially means that you're talking about the time that your aircraft can be operational based on the amount of fuel that you can put in. So you have the same equation, just divided by the flight speed, and you will get, you can simplify the equations further, get to this equation. Again, all of the equations you are going to get, most of the questions, not the equations, most of the questions you are going to get for this chapter is mainly going to focus on just plug and chug. So you plug the values you have, calculate the thrust, and then calculate all the other parameters and calculate the range and endurance and all of these things. And you can see a lot of those equations in your homework that I have already posted yesterday. Maybe that I've posted on September 14th. The last part we want to talk about is the modern engines that are being produced and manufactured and are already produced in the system. This is an example of the V2500 engine cutaway. And the engine, this is a cutaway of that engine. You can see all of the complex parts. You can see the compressor, turbines, and the exhaust parts of the engine. It's a very complex parameter, but eventually what you get is the same parameter that we discussed here for most of them, right? For example, for each engine, let's say this is your engine V2535A5, for example, you get the engine type. This is a table that you always get. Let's say you want to go out and buy a jet engine. This is a table they're going to give you as their engines they have in a stock, for example. You have the engine types. You always get the number of fans, low pressure compressor, high pressure compressor stages, also the low pressure and high pressure turbine stages, combustor types, a lot of other ratios. The weight of the engine is very important, and a lot of other parameters. So this is something that you will get. In this table, we don't have the TSFC and the specific impulse, but if you were to really buy these kind of engines, you would be interested in those as well. So this is going to be the final slide on chapter 3 from on Wednesday, September 16. We are going to solve some example problems from chapter 3. We are going to solve the problems of quiz 1 on Wednesday, and you will. I have to make this announcement. So in class, we have decided to have quizzes every week, right? So 1 hour quiz, only 1 question instead of 2 questions, right? To make it easier. And I will post a homework for you guys to practice whatever you want to practice, essentially each week from now on. Short homeworks, of course, like 2-3 problems maximum. But so the number of homeworks and quizzes are essentially going to be more than doubled. But there will be very short homeworks and very short quizzes. So make sure to reach out to me if you have any questions about this. And yeah, have a good rest of your day. And we'll see you guys later.